All right. So exponential models with differential equations. That's today's topic. Honestly, there's a lot of crossover here from stuff that you guys have learned in functions. So it's not all that different. There's just a little more terminology with the fact that we can actually solve these things using calc. To kind of just point out what's going on here, you kind of have two options with these problems. The goal of this lesson from AP standpoint is that when you realize you have an exponential differential equation, you can jump right from the differential equation to the solution without showing any work. That's the type of thing this is. Like, you know what oh, I've got exponential. That means that I can use the solution without showing any work to get there. In practice, if you don't realize that and you just do separation of variables, it's not a super hard problem to solve. So in the end, if you just end up solving it, no big deal. There are two topics like this, one in BC. There's this one and another one. The other one's kind of a bear to solve on your own, so you kind of have to jump to the solution, but this isn't BC, this is AB. We've got the easier of the two. So there are some differences. We'll talk about them as we go along. So back in pre-calc, when you learned about exponential growth or exponential decay, you had the general equation y equals some quantity a times some other quantity being raised to a power. A is your starting amount. And yeah, and if you're talking about money, it would be your principal. Amount. You're starting amount. Yes. A is your starting amount. We'll define amount later. And then B is your growth or decay rate. So it's a growth rate if B is greater than 1, and it's a decay rate if B is less than 1. The main difference between what you guys do in functions versus or pre-calc versus what's going to be going on in calculus is B isn't going to be B. It's always going to be E. Calc. Apparently my hand doesn't want to spell today. In calc, rather than having B, we're going to have e to the kt. And that really is two separate things. That is, I'm going to put this in parentheses, that is e to the k times e to the t. Actually, no, sorry, I'm wrong on that one. That is e to the k to the t power. That's the correct way to do that. I was thinking of what we were doing last week. And that's what your e to the k takes the place of b. So rather than having a different base depending on the problem, we're always going to use e, and then our t variable is going to have a coefficient, and that kind of takes the place of b. Whenever you have an exponential model, you have this situation, which is in this box. I don't think this is a very user-friendly sentence, but it does explain the situation. Whenever you see a problem where you're told that the rate of change of something is proportional to that exact same thing, you have exponential growth. That's really the key. The differential equation is the rate of change of something, and then the other side of it is just a coefficient times that something. So that really is what's going on here whenever you have exponential. And like I said, when you see yourself in that situation, you're allowed to jump right to the solution, or depending on what the question is asked. So examples of word problems where that happens. Number one, the weight of an animal is increasing at a rate that is proportional to its weight. So it really is just the same variable twice. That's how you identify exponential growth. So we would write this as maybe dw dt equals kw. And you can see this really connects all the way back to what we did in G1 with kind of just making those proportions. If this is your situation where you're at dw d something dt equals k, that exact same something, you have exponential growth. Number two, a bacteria population is shrinking at a rate proportional to its population size. maybe we'll use d capital P dt, and we'll call that kp. The shrinking will just make, if it's shrinking, you're just going to end up with a negative number for k if you were actually solving for that k. So you don't need to do anything different between growing and shrinking. It's just when you solve for your k variable, you'll get a negative, and then obviously dp dt will be a negative value anytime you plug a population in. Okay, this is super easy to solve. We'll find our solution. So any one of these, replace the w, replace the p with dy, or with a y, I should say, and we get this differential equation, which, changing it into the language of integrals, gives us dy over y equals k dt. Anybody have any issues with that? Makes sense? And then when I integrate, on the left I get, ln absolute value of y, and on the right I get kt. Boom. And then, not just kt, but kt plus c. Yep. So again, worst case scenario, you didn't identify that your problem was something you just knew the answer to. You do this one step. If you're in problem 1, you have w where all the y's are. And then this is pretty much, hopefully, just kind of autopilot. We'll exponentiate both sides. And that gives us, capital C e to the kt. Now, there's extra steps in there. I could have written y equals absolute value of y equals e to the kt plus c, and then pulled that c out. But hopefully, from the practice, once you exponentiate something, that's always how it's going to happen. That plus c is going to come to the front as a coefficient. And hey, look, that's what the answer says in the box. All righty. Okay, so find the particular solution for each differential equation. So again, the goal here being that once you realize that the right-hand side of your differential equation is just a coefficient times the y variable, or whatever the story problem variable is, you can go right to the solution. Oh, this is exponential. I can say I know that the answer is y equals capital C e to the 6t. You do need to identify that k equals 6. And then they just gave us initial condition. So y equals 5 when t equals 0. So y of 0 equals c e to the 6 times 0 equals 5. And then that just basically gives us capital C equals 5, because e to the 6 times 0 is 1. So our final answer here is y equals 5 e to the 6t. That represents growth because our k was positive. The next situation represents decay because our growth is, or because our coefficient is negative. Same deal, super easy. Y equals c e to the negative 3t. Y of 0 equals c e to the negative 3 times 0, which equals 4. So c equals 4. Same thing, right? They're both the same thing. It's just that number ends up being your c, as long as x is 0. All right. Number 5's got a little more going on with it. In number 5, we're actually going to need to find both the C and the K. They're not going to give us either of those, but they are going to give us 2 points on the 2 points that satisfy the solution. So we'll use 1 point to solve for K. We'll use the second point to solve for C, just like we did up at the top. So kind of show you how this works. An animal weighs 3 pounds at birth and 4 pounds just 3 months later. So those 2 sentences, 3 pounds at birth, they're telling us that our t-value is 0 and our weight variable is 3. So that represents the point 0.03. And the second one represents the point 3, 4. Yeah. So time is usually, whenever we're working with these, is going to be our x variable, our independent variable. And then whatever we're measuring is going to be our y variable. The next part, the weight of the animal is increasing at a rate proportional to its weight. Once you see that, that's too big. Once you see that, that tells you you're dealing with exponential. So we've got the weight is proportional to the weight. So we can write dw dt equals kw. And we know immediately that the solution to that is w equals e to the ce to the kt. But they never gave us the k. What they have to do is they have to give us the initial, because when I plug that first point in, the orange point, I'm going to do e to the k times 0. That's going to allow me to solve for c by itself, because it's going to kind of wipe out the k variable. So watch how that works. So we'll start in orange. We'll say the w of 0 equals c e to the k times 0. And then that equals 3, because the w of 0 is 3. But even though there's a k there that we don't know, we do the same thing we did up at the top, and we find out that c equals 3. Now we can jump to the blue quantity, or the second point, and solve for k, because we know that c is 3. So the w of 3 equals 3 e to the k times 3, and that equals 4. So I've plugged in 2 different 3's there. We know that the capital C is 3, and we know that the, in this case, the x value or the t value is 3 as well. Plugging that in gives us 4. Alrighty, so we can solve that. We get e to the 3k equals 4 thirds. Ln both sides. And we get 3k equals ln of 4 thirds, or k equals ln of 4 thirds divided by 3. We can write our final answer. Might take us 1 or 2 lines here. So we end up with y equals 3 e to the ln 4 thirds over 3. That's what I'm going to get to next. Yep, no, you're good though. Ln 4 thirds over 3 t, e to the kt. All right. So what we can do here is we can, I'm just trying to figure out how much I want to show. This is the same as e to the ln 4 thirds to the t over 3. So with that, we can now change our base back 3 4 thirds to the t over 3. So basically what I did was I separated this exponent. It's a bit of a messy exponent. I kept the things that weren't ln's together. So t was a numerator, 3 was a denominator. So I kept the t thirds as my exponent, but I separated the ln 4/3, and e to the ln of 4/3 is just 4/3. Okay, so there are a lot of different things there. There's one more example to do. It's doubling in half-life. Half-life? Yeah, you know. Yeah, you know, just a little bit too practical for my liking. But so we'll do that. We'll do that tomorrow. We'll start off class tomorrow with that one. Yeah.